Objective 2.8, the Fundamental Theorem of Algebra. In this lesson, we want to use the Fundamental Theorem of Algebra to determine the number of zeros of a polynomial function and then be able to find all of the zeros of a polynomial function. So up until this point, in our previous lessons, we've been trying to find certain kinds of zeros, the rational zeros or the real zeros. Now we're going to be looking for everything, every possible zero that we can get. So just a little bit of vocabulary as we get started here. A factor that appears twice or more, doesn't have to be twice, in a factored equation is called a repeated solution. And we need to keep that in mind, that sometimes zeros and solutions will be repeated. They'll happen more than once. Okay? All right, so here's the theorem. And this always makes me giggle just a little bit because this fundamental theorem of algebra sounds like such a big deal. Like if you understand this theorem, all wisdom about algebra will be opened up to you and you will know all of the secrets behind how to do algebra. I mean, it just sounds like it's this huge big deal. Well, basically what it says is this. If f of x is a polynomial of degree n, where n is greater than 0, okay, so that fits the definition of what a polynomial is, then the equation f of x equals 0 has at least one root in the set of complex numbers. Now keep in mind, the set of complex numbers includes all real numbers as well as imaginary numbers and full complex a plus bi kinds of numbers. So it's saying it has to have at least one root in that set of numbers. Well, that kind of sounds like a no-duh moment. It doesn't sound like it's that big a deal. And even if we extrapolate from that a little further, the general statement that is based on this fundamental theorem is that when all the real and imaginary solutions are counted, with all repeated solutions counted individually, then an nth degree polynomial has exactly n solutions. Another way of saying that is an nth degree polynomial function has exactly n zeros. So again, we know from previous lessons that solutions and zeros are related to each other. And so what we're allowed to come away with from this theorem is the fact that if we have an nth degree polynomial, we will have exactly n solutions or exactly n zeros. Okay? All right, so again, equations have solutions and functions have zeros. So if I give you the function f of x equals x to the fourth minus 2x cubed plus 10x squared minus 18x plus 9, I'm asking you how many zeros will this function have? If we're counting all of the possible zeros, how many would we expect? Since this is a fourth degree function, we would expect that there would be 4 zeros. And so that's what we're going to be looking for as we try to solve all of the zeros, as we need to end up with 4 of them when we're done. So let's start finding them. Now, the starting place is just like what we talked about before. We want to make a list of the possible rational zeros and test those first. So in this case, we've got our constant of 9. So the factors of 9 would be plus or minus 1, plus or minus 3, and plus or minus 9. And then we have a leading coefficient of 1. So plus or minus 1 will be our denominator. So that means we have 6 possible rational zeros, plus or minus 1, plus or minus 3, and plus or minus 9, that we're going to start with to start testing and see if any of them work. So let's start using synthetic division and test things out. And so as we start testing, we find that positive 1 is a 0 because we end up with our remainder of 0 right here. And so that tells us that positive 1 is going to be a 0. And it tells us that we have this reduced polynomial with coefficients 1, -1, 9, and -9. That means that our reduced polynomial has a degree of 3 because we started with a degree of 4 divided by a linear, so that decreases the degree by 1, and we now have a cubic as our reduced polynomial. Well, the cubic isn't something that I'm excuse me, that I'm very good at factoring yet, so I'm going to continue to test numbers using that reduced polynomial. Okay, so we're just going to move things up here a little bit so we have a little bit of room. So I'm going to keep testing the numbers in my rational zeros list. So maybe we try a -1, and we can see that -1 is not a 0 because I get a remainder of -20. So maybe I try a 3. Again, 3 is not a 0 because I get a remainder of 36. 9 seems like it's getting a little big, so I'm going to go back and maybe just try a positive 1 again. And you'll notice that if I try positive 1 again, it does give me a 0 remainder. So this is what we call a repeated 0. The fact that we're using positive 1 twice in order to work this down to a reduced polynomial that is now quadratic. And that quadratic is x squared plus 9. All right, so if we now rewrite our function in factored form, we've got x minus 1 as a factor from one of the ones. We've got x minus 1 as the factor from the second one. And then we have the x squared plus 9 as our third factor. So now to find the zeros, we're going to set each factor equal to 0 and solve. So x minus 1 equals 0 will give me x equal to 1. I do that again with the second x minus 1 factor, so there's another x equal to 1. And then I set my x squared plus 9 equal to 0. And notice that I had to subtract the 9 to get x squared by itself. So when I take the square root of both sides, I end up with the square root of -9, which ends up giving me 3i. And remember, it's plus or minus because when I square root as part of solving an equation, it's always plus or minus. And so my actual zeros are 1, positive 3i, and negative 3i. So these are including all of the possibilities. We've got the real numbers, we've got the imaginary numbers, and keep in mind that 1, even though we're only listing it once, it is a repeated 0. It really counts as 2 distinct zeros, and therefore we really did get 4 zeros in total like we expected. All right, so why don't you give one a try? Notice you have 2 questions here. First of all, they're asking you how many zeros you would expect in this polynomial function, and then they're asking you to go ahead and work it out and try to find all of the zeros for the function. Pause the video for a moment while you're working, and come back when you're ready to check your answer. All right, so since we have a 4th degree polynomial, we would expect 4 zeros. And what you should work out is that the zeros are going to be a positive 2, a negative 1, and then when you get that x squared plus 1 equals 0 for your quadratic, you can end up with plus or minus I from that factor. So again, 4 zeros, the 2, the negative 1, the positive I, and the negative I are what we get for the answer to this function. All right, now let's turn that around. So instead of giving you the function and asking you for the zeros, what if I give you the zeros and ask you for the function? Now there are a lot of possibilities of what you could really get if you just know zeros. So we're trying to keep it as simple as possible. We're being asked to write a polynomial function of least degree, which basically says we're not going to assume that any of our zeros repeat, that has real coefficients and a leading coefficient of 1. So again, we're not going to be multiplying by any constant to make it something more complicated. So if I tell you that you have zeros of -1, 5, and 6, you should be able to come up with the fact that we would have factors of x plus 1, x minus 5, and x minus 6. Okay, again, that comes from that property, I guess you could call it, that we saw in a previous lesson that said that the 4 different statements were all equivalent. So if we know what zeros are, taking x minus those zeros give us factors. So we now know what the factors are. And then we just need to multiply the factors out to get the polynomial in standard form. So if I take x plus 1 times x minus 5 first, that ends up giving me the x squared minus 4x minus 5. And then I can take that times the x minus 6. And I ultimately end up with x cubed minus 10x squared plus 19x plus 30. Now keep in mind, because this is multiplication, and multiplication is commutative as well as associative, we can move the order around. It doesn't matter what order you put them in. We can also decide to take the x minus 5 times x minus 6 first, then multiply by the x plus 1. Any of those are legitimate ways to get to our final answer, and you should always get to the same final answer. Now, what if I tell you that the zeros are 2, -1, and 3i? Now, here's a little tip to help you with these. When we have complex zeros in a polynomial function with real coefficients, that has to be a condition, and that is what we're being asked for, then we always know that the complex zeros occur in complex conjugate pairs. So you remember complex conjugates from the previous chapter? So that means that if I know 3i is a 0, I automatically know that -3i also has to be a 0. So I'm going to add that to the list and then set up my factors from that. So as you work through this, you'll see that we've got x minus 2 from our 2, x plus 1 from our -1, and then x minus 3i. We do the same thing even with the imaginaries, and x plus 3i from that one. Now, I would always recommend that you multiply out the factors that have the imaginary zeros first, because it's going to get rid of the i's for you. So in this case, we really just have a sum difference pattern. So we're going to take the x squared minus the 9i squared, and then I squared becomes -1, and so that's how we get x squared plus 9. Okay, then we can start multiplying the other factors together. So maybe we take x minus 2 times x plus 1, which gives us x squared minus x minus 2. And then finally we can take that times our x squared plus 9. And when we multiply it all out and simplify, we end up with x to the 4th minus x cubed plus 7x squared minus 9x minus 18. Okay, so just lots of practice and foiling and distributing and superfoiling in order to get to our final standard form polynomial. All right, so why don't you try one? if you have the zeros 3, -3, and -2, what is the polynomial function of least degree with real coefficients and a leading coefficient of 1? Pause the video for a moment while you work this out and come back when you're ready to check your answer. All right, so let's check it out. Our zeros tell us that we have three factors, x minus 3, x plus 3, and x plus 2. If I multiply the first two factors together, they follow the sum difference pattern, so I can get x squared minus 9 from that. And then I can multiply that with the x plus 2 to get x cubed plus 2x squared minus 9x minus 18. All right, so that's what you'll be doing in your practice problems for 2.8. Some of the problems will give you a function and ask you to find all the zeros of the function. Other problems will give you the zeros and ask you to use the factors in order to come up with what the polynomial function should be. If you have any questions on this, make sure you're finding the resources to help you answer those questions. Send me an email if you need to. Talk to Mr. Fairking, talk to other teachers, look online, go back to the video. And don't forget to check your completed answers on Canvas to make sure that you really are on the right track and showing the right work. And if you have any questions or issues, make sure you let me know by email. And we will see you next time.